basically Markov chain means that we are talking about a sequence or a stochastic process of discrete random variables. So if you fix the index of the random process, basically you have a discrete random variable that can take finite or countably infinite values. And the index of the process itself will be a non-negative integer, okay? Now, the values taken by the random variable x of n. So again, once you fix n, your random process, now we are talking about a specific random variable x of n, and it's discrete. And so, you know, it takes values from a set S, which can be finite or countably infinite. And basically, the values in the context of Markov chains are typically referred to as states. Okay, so the states, when I say that the Markov chain is in this state at instant 5, you know, so I'm talking about x of 5, and by state I mean, you know, one of the possible values that can be taken by x of 5. Okay, so the values taken by the discrete random variables that compose the discrete-time Markov chain are called states. The Markov property, as we defined it last time, means that given the present, the future, and the past are conditionally independent. And this means that if you have basically two events, so this is an event that depends on x of n plus 1 up to x of n plus m, and another event that is defined in terms of x of 0 up to x of n minus 1. So now these two guys are generally, they are dependent, but given that x of n is equal to I, these two guys, so given that x of n, so here we have x of n, those are from x of n plus 1 to x of n plus some finite number m, finite integer m, and this is from 0 to n minus 1. So given x n is equal to I, then these two guys become conditionally independent of one another. Okay, let's have more definitions and introduce some notation. So the probability that x of n is equal to I, so I is a value, and typically the values taken by the discrete random variables of a Markov chain, you know, you can call, you know, you can, these values can be, even if they are like sort of not integers, you can by the end of the day, you know, change their names or their labels or whatever and call them integers, okay? So typically we'll be in a situation like this. We ask ourselves about the probability that x of n is equal to I, and so that's the probability that the DTMC is in state I. So, you know, here what I was saying at the beginning of the lecture, which is that when x of n is equal to I, you know, so the values taken by those discrete random variables are typically referred to as states. So here is the question that at time instant n, what is the probability that the discrete-time Markov chain is in state I? And so this can be written like this, or it can be written as b of n and a subscript that is I. Now we can have something that is like more complicated. So now we have a subscript I and j, and then we have two parameters m and n. So now we are talking about a so-called transition probability. Transition probability. And you see that there are four things. There are two time instants, and then there are two states or two values. So specifically b, and then as a subscript I and j, and then as a superscript m and n, this is the probability that at instant m, x of n is equal to I. So given that, so this is an event that we condition on, given that we ask ourselves what is the probability that at instant n, x of n is equal to j. Okay, so b, I, j, and then m and n, this is the probability that x of n is equal to j. Okay, so x of n, so this guy here, is x of n, so this is the time instant is equal to j, but it is conditional probability. Here we condition on something, which is that at x of m is equal to I. So this is basically given that the discrete-time Markov chain at instant m, it is in a state I, you ask yourself now, what is the probability that it will make a transition? It will go from state I to state j at instant m. And so this thing here, again, it can be written as this probability. It can be written as B, I, J, and then M and N between brackets on the line, or as a superscript. Again, we have like several ways of writing this down. But the idea is that you have four parameters. Again, 2 time instance and then 2 states here, I and J. Now, in this course, our interest, and actually in practical applications, most of the discrete time Markov chains of interest are homogeneous. And homogeneity here refers to a very specific thing, which is that basically, if you ask yourself what is the probability that at instant k the chain is in state I, so xk is equal to I, and given that, what is the probability that xk plus n, so this basically is the n time instant is k plus n, here it's k, that this is equal to j, okay? So this is something like this, and generally speaking, for a general discrete time Markov chain, this would depend on 4 things. It would depend on k, it would depend on n, and it would depend on I and j. For a general Markov chain, but our interest will be homogeneous. So so it's like, if I don't mention the word homogeneous in any context, whether it is in a lecture or in a homework problem, then automatically your Markov chain is homogeneous. So again, I don't have to, it's the default, and most likely it is the only thing that we will study here. So homogeneity means what? That this probability, which generally depends on 4 things, actually it depends on just 3. So it will depend on I. So for homogeneous, this will depend or depends on I, okay, J, okay, and then N, just N, which is the difference between these 2 time instants. The difference between these 2 time instants, okay? So this probability, it doesn't depend on K. And this is true for every k, that is that is a positive or a non-negative integer. Okay, so if basically this transition probability, the conditional probability that the discrete time Markov chain at instant n is in state j, given that at instant m it is in state I, if basically this probability just depends on the difference between n and m, or here written in this way, it will depend on the difference between k plus n and k, which is n. If this is true, then basically we say that we have a homogeneous chain. And so when you write it down, you write something that depends on 3 parameters. So B, I, J. So basically I, that's the state you are conditioning on. J is like sort of the state you are going to. And then as a superscript, you write the time difference. You just write the time difference because it is what really matters. Okay, and so here the superscript will be just n. Okay, and so in that case here, the probability that x1 plus n is equal to j, given that x1 is equal to I, is exactly the same as the probability that xn is equal to j, given that x0 is equal to I. And again, you can put k, you can set k to any non-negative integer value of your choice. Okay, so as I said here, unless otherwise stated, the focus, whether it is mentioned explicitly or not, will be homogeneous discrete time Markov chains. Okay, of interest is basically probabilities that look like this, the state transition probabilities, in which small n, which is the time difference, is just 1. Which means that you are typically like, you are currently in, the Markov chain is in a certain state, and you ask about, what will happen immediately in the next step. Okay, so those are basically the probability that x of n plus 1 is equal to j, given that xn is equal to I, and this does not depend on n for a homogeneous discrete time Markov chain. It will depend on I, it will depend on j, and the time difference is 1. Okay, so it can be written like this with the superscript with 1, or if I eliminate the superscript, then it is understood. If I write just bij without a superscript, it means that this is an investigation of a time difference of 1. Okay, so it can be written in those three ways: Bij of 1, or Bij superscript 1, or just Bij. So that's because basically we are talking about going from we study x of n, and then given that we study x of n plus 1, it's called the one-step transition probability from state I to state j. The one step, moving just in one step. So you are the chain is in state I at instant n, and then just after one step at instant n plus 1, it is in state j. So again, it is something that it turns out that actually those probabilities are very important for homogeneous discrete time Markov chains. Okay, and we can obtain the general probability. So here, if the time difference is something other than 1, we can obtain them if we know those probabilities here. Okay, then we can have a B of n without any subscript. So this is basically a collection of the state probabilities at instant m. So basically, this is a row vector that contains, basically the probability of the various states depending on what your states are how your states are defined, and then all of them at instant m. And again, don't forget that this word state is nothing but the values taken by the random variable x of n. Okay. Again, here they are called states. Now, if we go back to the one-step transition probability, again, I said this a number of times. If you find something and it depends on two parameters, specifically they are like two positive integers or two non-negative integers, like it's very tempting to think of a matrix that contains those parameters. And so if you have Bij, you may say, okay, I mean, it looks like we can define a matrix here. And so indeed, in the topic of discrete time Markov chains, we define the P matrix, which is the TPM. So transition probability matrix, and it's a matrix whose elements is I and J. Okay, so we can also describe the discrete time. So this matrix is very important in characterizing a discrete time Markov chain and a homogeneous one. And also, we can describe the discrete time Markov chain using a signal flow graph, a diagram that looks like this. Okay, and so now we have basically our case here. The state space is 0, 1, 2. So basically, our discrete random variables in this example, they can be 0 or 1 or 2. Okay, and this is the transition probability. So again, here the states will be 0, 1, 2, and this will be 0, 1, 2. And so this 0 here means that if you are in a state 0, the probability that you go to 0 is 0. If you are in a state 0, the probability of going to state 1 is 1. If you are in a state 0, the probability of going to 2 is 0. This 1/4 here means that if you are in state 1, the probability of going to 0 is 1/4. So like, let's write this explicit. So this tells you that the probability that x of n plus 1 is equal to 0, given that x of n is equal to 1, this is equal to 1/4. Okay, and so on. Okay, so this will be basically the TPM, and it tells you those one-step transition probabilities. And note that the sum of each row is equal to 1 for the obvious reason that given that you are in a certain state, you will need to go to some state in the next time step, right? So basically, the probability that x of n plus 1 is equal to j, given that x of n is equal to I, and suppose that you sum this thing, j is in the state space, then this is equal to 1, which simply means from state I, so the Markov chain now, basically the value of the discrete random variable is I. From state I, you need, or not you specifically, the discrete time Markov chain goes to some other state, including I itself. You can make a, basically you can be an I and have a transition. So let's look at this one. This 1/4 here. This 1/4 here means that the probability that x of n plus 1 is equal to 1, given that at x n is equal to 1. So here there is, with probability 1/4, the discrete random variable at some time instant is 1, and then in the next step it's also 1. Okay, so self transitions are possible. But again, the thing here to focus on is that if you take the TPM, so the TPM is like, each row you are conditioning on some state, and you are giving the probabilities that given that state, what is the probability of making a transition to another state. And so the sum of all those guys should give you 1. Again, in a compact form, this will be that summation j. So bij, so this is basically the transition probabilities from I to j, this should be equal to 1. And don't underestimate this property, because now you have a matrix and the sum of its rows is 1. Okay, then we can actually make conclusions regarding that matrix, as we will do basically next. Okay, but before doing that, the TPM is a nice way of representing a homogeneous discrete-time Markov chain. And another way, again, both are useful, is basically a state transition diagram or flow graph, in which you represent the states like with vertices, and basically you have arcs connecting, so it's like a directed graph, and basically the arcs will tell you the transition probability. So 0 to 1 with a 1 here, it means that if you are in state 0 with probability 1, you will go to state 1. So basically this first line here, which is 0, 1, 0, it exactly tells you this, that if you are in state 0, then it's inevitable that the next state will be 1. Okay, but what if you are in state 1? Well, in that case, with probability 1/4, you are with probability 1/4, you will go to state 0. So this is the first 1/4 here. Then the second 1/4 is the self-transition probability, and then with probability 1/2, you will go to state 2. And then finally for state 2, there is 0 probability that you go to 0, so we don't draw anything. And then with probability 1/2, you go from 2 to 1, so that's 1/2. And then with probability 1/2, you go from 2 to 2, so basically this is a self-transition with probability 1/2. Okay, again, this is useful, that is useful, and and typically in problems, and if you even use Markov chains in your research, both those representations are very useful. Of course, the set space representation, especially if you have a few number of states, and you can basically draw the whole thing and imagine what is going on. This also is good, and you can go from the TPM to the graph, and from the graph to the TPM. Okay, any questions? Okay, I know people who took 241 in the previous course, basically you already know this stuff, and actually the discrete-time Markov chains, especially if you have a finite number of states, actually is like an undergraduate subject. So in some universities, basically undergraduate students know actually how to do Markov chains, especially for if the number of states is finite. Okay, which means that the discrete random variables take finite values. The technical challenges are basically when we have an infinite number of states, and we will see this. So P is a matrix. It's called a Markov matrix or a stochastic matrix. You can call it Markov or stochastic. Again, it's not an arbitrary matrix. It's a matrix of probabilities, and so the elements are non-negative. So that's one thing, and also each row sums to 1, as I explained on the previous page. Okay, so if you have these two properties, then your matrix is Markov or stochastic. Okay, now this is one implication of this, is that if you take the matrix B and you basically multiply by the all one vector, column vector, what will happen? So when you take a matrix and multiply by the all one vector, you basically get another vector, and in the other vector here you get the sum of first row, and then you get the sum of second row. This is general, right? If you take a matrix multiplied by the all one vector, then you get a new vector whose first component is the sum of the elements on the first row of the matrix, second component the sum of the elements on the second row, and so on. And those sums for matrix P, the TPM, are all equal to 1, and so this is equal to D. Okay, and so basically, if we take the transition probability matrix multiplied by the all one vector, we get back the all one vector. But I can rewrite this, you know, in a like another way. I can put BD is equal to 1D to emphasize that we have an eigen equation. Okay, so basically, what this is saying that your transition probability matrix, now we know that it has an eigenvalue of unity of 1, and the associated eigenvector is the all one vector. So any transition probability matrix is guaranteed to have an eigenvalue that is equal to 1, and basically if we are talking about the right eigenvectors, the corresponding or the associated eigenvector is the all one vector. Okay, and this is again because the sum of each row is equal to 1. Okay, now we know that basically if a matrix, you know, a matrix and its transpose, they have the same eigenvalues, and this is clear from the characteristic equation. So if you know, we can say it another way, that if P has an eigenvalue of 1 with an associated right eigenvector that is equal to the all one vector, then there is also another vector, you know, so this is called the left eigenvector, that if you multiply by P, you will get also 1 times pi, which is pi, right? Which is another way of saying, so this is a row vector. Again, the way to see this, if it looks confusing, is just to take the transpose of both sides, and so this is P transpose pi transpose is equal to 1 pi transpose, which tells you that, well, if 1 is an eigenvalue of P, then 1 is also an eigenvalue of P transpose. And the eigenvector is, you know, is generally speaking something different from the all one vector. Okay, so this is another conclusion. Here I call it Q. So there is another a left eigenvector, which is a row one. Okay, it's a row vector. You know, and again, like rather than like doing things with the transpose, typically the notation is that we will you know, consider vectors that are multiplied from the matrix from the left, and those are row vectors. Okay. So there will be this this vector, and this is guaranteed. This is guaranteed for basically all finite dimensional matrices. So for every finite dimensional matrix, you are actually guaranteed to obtain, you know, those eigenvectors. But it's not the case for infinite dimensional matrices. So if the number of states, so what is the dimensionality of the transition probability matrix? It is let's say K by K, where K is the cardinality of the state set S. But this set can actually be countably infinite, and so actually the matrix can be infinite dimensional. Okay, so for infinite dimensional matrices, you may not find a solution to the eigen equation. This is something that is not true for finite dimensional matrices. For infinite dimensional matrices, so this is a matrix, okay, and which is this one here, and it is a valid Markov or stochastic matrix. The elements are non-negative, and the sum of each row is exactly equal to 1. It is a transition probability matrix, and this is, if you draw the diagram of this discrete-time Markov chain, it's like if you are in a state 0, so let's say the states are called 0, 1, 2, and so on, with probability 1, you go to state 1, and then if you are in state 1 with probability 1, you go to state 2, and then if you are in state 2 with probability 1, you go to state 3, and so on. Again, that's a valid discrete time Markov chain, and it is basically the number of states is the cardinality of the set of non-negative integers, which is elif note. Now, let's try to basically find, or solve the eigenequation of this infinite dimensional matrix. Okay, so let's suppose that we have a Q vector. Now it's a row vector that is also infinite dimensional, and that satisfies QP is equal to 1 times Q. So just to basically do it, write down the vector multiplied by the matrix is equal to the vector, and let's now try to solve it. Now the first column in the matrix is all 0, so if you study the left-hand side, you will take this row vector and multiply by this column, so every entry here will be multiplied by 0, and you just get a 0. Now you equate this to the first element, Q0, so Q0 is 0. So Q0 is equal to 0, okay? And then you go and study basically the multiplication of this row vector with the second column, and so everything in the second column is 0 except the first guy, which is 1, and so from the left we have 1 times Q1, which is Q1, and we will have 1 times Q0, which is Q0, right? So because it's the first here, the first element is 1, will be multiplied by Q0, and then every other Q will be multiplied by 0, so that's a Q0. But from the right, this is equal to Q1. So Q0 is equal to Q1, but from the first step, we have that Q0 is equal to 0. So Q1 is equal to Q0, so Q1 also is equal to 0. And you keep doing this, and then if you want to find the vector that satisfies the eigenequation QP is equal to Q, it will be the all 0 vector. And the all 0 vector is not, by definition, an eigenvector, because an eigenvector must be a non-zero vector. Okay, and so basically, this will make a difference. It make a difference between finite dimensional matrices and infinite dimensional matrices. And in our context here, finite dimensional matrices are related to basically discrete time Markov chains in which set S is finite or has a finite cardinality, but infinite dimensional matrices will be associated with discrete time Markov chains in which S is basically it has a cardinality elif note. And so yes, I mean the eigenequation may not be basically it may not have a solution or a corresponding eigenvector if in the infinite dimensional case. So keep this in mind, and this tells you that it's not always the case. It's not always the case that you can do something in finite dimensions and generalize it to infinite dimensions. Sometimes there is a gap. Sometimes there is a break, and sometimes you get something new when it comes to infinite dimensional space. Okay, and those are important. Those are important to us. Can we have an infinite cyclic chain? What do you mean by cyclic chain? You mean like from 1 to 2? Last one back to 0. So you have a transition that looks like this. I mean, well, you can imagine that this is what you have, right? But if I want to specify the transition probability matrix, well, what I want to do is that I will specify it for any finite for any non-negative integer. Right, so infinity is not an integer, which means that it's if I say that the states here are the non-negative integers, then basically I need to specify the row corresponding to each non-negative integer. And so so if you have something in mind, it's basically this is what you get. Right, because we don't really have infinity and then because infinity is not actually an integer, right? But here you have something like goes like this, okay? And it's like an extreme case, but it's an extreme case, but it makes the point that again, something that we will see again and again. I think like in this lecture, we will, for example, prove that every finite discrete time Markov chain, it has something called an invariant distribution. And it is for, for infinite ones, no. You will need like more conditions to be able to guarantee the existence of an invariant distribution and so on. So, so again, like there is like sort of a disconnect between the finite and infinite dimensional cases. Okay, now let's move to the other topic. Any questions? Okay. Now, what is the, so this is, remember from the notation, this is what is the probability? What is the probability that x of n plus 1 is equal to j? What is the probability that, the chain at time instant n plus 1 is in state j, which means that the discrete random variable x sub n plus 1 is equal to j. Now, can we write down this thing? Can we write down this thing in terms of the like the previous state? Yes, I mean the law of total probability. So this thing is equal to summation I, right? Summation I, and I belongs to the state S. And then you have here the probability that xn plus 1 is equal to j, and x of n is equal to I. Right? So this is like law of total probability. Okay, nothing, and basically even if the state is countably infinite, no problem. And then what I can do is that I can take this joint probability and, as and I can write it like, this joint, I can write it as probability that xn plus 1 is equal to j, given that x of n is equal to I, probability that x of n is equal to I, which is basically here. So the probability that the chain at time instant n plus 1 is in state j is the probability that at instant n the chain is in state I, and then it makes a transition from I to j. Remember, this thing is basically the transition probability from I to j. Given that x of n is equal to I, this is the probability that x of n plus 1 is equal to j, which sort of makes sense. Okay, so again, state at the probability of being in state j at instant n plus 1 is a summation over all possible states of being in state I at the previous instant of time, and then making the transition from I to j. And now I can collect those guys. In row vector. Remember, I can have like this row vector here, in which like you have bj minus 1 n plus 1, bj of n plus 1, bj plus 1. Again, if assuming that the states are basically the non-negative integers, and I can write down using this equation, I can say that this row vector is equal to basically the transition probability is equal to another row vector, which are basically the states at instant n. Okay, and then this thing is multiplied by basically the transition probability matrix, the TPM. Okay, so if you look here, let me change the color and focus on something. Let's look at this thing. So it's bij, bij. So here, like if you want basically to study j, what you do is that you take this row vector with the probabilities at instant n, and you multiply it by basically the jth column. Right? So this is a summation over I. I will sweep through the possible state values, and what you do is like a pin times pij. So again, like it is basically this matrix equation. You can collect all those state probabilities in this row vector. So those are the state probabilities at instant n plus 1. So we can write this as the state probabilities at instant n, and then it's multiplied by basically the transition probability. Again, something that may look annoying is that, like in some fields, basically the default vectors are column vectors. And we typically, when we multiply matrix by vector, it's like the matrix and then the vector is to its right. But, like in discrete time Markov chains, actually our vectors mostly will be those row vectors that are multiplied by the matrix from the left. Okay, and we will just stick to this classical notation. Okay, so Bn plus 1 is equal to Bn multiplied by P. So you can basically iterate, right? You can basically iterate this thing. So you can say what, that, Bn plus 2 is Bn plus 1 times P, but Bn plus 1 itself is Bn times P. And so now so Bn plus 2 is equal to Bn times P squared. Or you can go further and prove that, the state probabilities at instant n plus m is equal to basically the state probabilities at instant n multiplied by the transition probability matrix raised to the power m. And so m will be basically the difference between these two time instants. Okay. And so if you look here, basically, let's write this as a summation. Perhaps it's like useful. So what we are doing here is to say, what is the probability that x of n plus m is equal to j? What we are saying, again, by applying the law of total probability, that this is the probability that x of n at instant n, the state is I, and then you do a transition, right? You do a transition in m steps to go from I to j. So that's the probability of x of n plus m is equal to j, given that x of n is equal to I. Right? So so this is basically, again, you can write down this thing, write down basically apply the law of total probability, and then write down the joint probability as a conditional probability times the probability of being in state I at instant n. But what is this thing? So at instant n, the chain is in state I, and then at instant n plus m, the chain is in state j. So this is basically the transition probability from I to j, right? But in m steps. And it will depend only on m, not n, because again, we deal with homogeneous discrete-time Markov chains. Okay, so basically this is what we get. And so here, we can write down this probability, the probability at instant n plus m. If we collect all those state probabilities at instant n plus m, this is equal to all those state probabilities at instant n multiplied by a matrix. And so this matrix of the m step transition probabilities. But what did we get by basically iterating our first equation? We got that Pn plus m is equal to Pn p to the power m. So that's actually nice. Those m-step transition probabilities, you can obtain them by taking the TPM and just raising it to the power m. You take the transition probability matrix, which again, don't forget, it is the one-step transition probability. If you take it and you raise it to the power m, you will get the m-step transition probabilities, which are the conditional probabilities that at instant n, you are in state I, and then after m steps, so specifically at instant n plus m, the chain is in state j. Okay, so so basically the b to the m is this matrix. Okay, so that's the reason that for homogeneous discrete-time Markov chains, like the TPM is sort of enough. If you want to know how, the probability of making a transition in any number of steps, just take the transition probability matrix and raise it to the required number. Okay, and basically you can do something here, which is it's a sort of a game. You can play with this thing, which take the transition probability matrix and raise it to the power m, and then you split this m into k and m minus k. We can do this, right? So p to the m is equal to p to the k, p to the m minus k. So remember, what are basically the elements of p to the m? Okay, so the elements of p to the m are the m-step transition probabilities. So element here, so this basically, if you take an element here, it will be like going from I to j in m steps, which is actually, let's write it explicitly, that x n plus m is equal to j, given that x n is equal to I. Now you can write it as basically, if you rewrite this matrix as a product of two matrices, then element ij in this matrix comes from multiplying row I in this matrix, row I, and column J in this matrix, which can be expressed like this. Okay, so Pijm is a summation over basically the state probabilities of Piv k to the k multiplied by bvj to the m minus k. So again, the probability that you, given that at some instant of time you are in a state I, the probability of doing a transition to state j in n steps can be represented as a summation over v in s of biv to the k, which means that you go from I to v in k steps, and then you go from v to j in m minus k steps. Okay, so like in words, let me actually write it like this. So I to j in m steps is like summation over v in s, and then you go from I to v in k steps, and then from v to j in m minus k steps, which looks like so intuitive. Okay, so you make a transition. You go from I to j in n steps, where you can think of it, of doing those, basically of doing this transition from I to j in n steps, as if you go from I to some state v in k steps, where k is less than m, and then you go from that state v to state j in the remaining number of steps, which is m minus k. And this is a family of equalities, because it is true for every I and j. So those equalities or equations are called the Chapman-Kolmogorov equations. You can think of them again as like doing this trick of taking a transition probability matrix and splitting it, or like you can do it again using like sort of a you start your derivation from scratch, and sometimes it's good to have something like this in mind. Why? Because this Chapman-Kolmogorov equation again is like sort of, it looks so intuitive that you will feel that it is something that is like universally true. You have going from I to j in m steps is it is like go from I to v in k steps, choose k from 1 to m minus 1, and then from v to j, and you just sum over v, right? But let's basically do it in slow motion and see that actually some assumptions are needed. Okay, and the assumptions are, we need a homogeneous Markov chain with the Markov property. This is generally not true if you have a random process without the Markov property. Okay, so in slow motion, bij to the basically m, and basically I when I have a superscript between brackets, to emphasize that this is not raising to a power or something. So this is again, you go from n, at instant n you are in I, and then at instant n plus m, so m steps later you are in j. Okay, so first, law of total probability, basically our friend forever. You just write down the law of total probability, and so what I will do is that perhaps like I said that I will do things in slow motion, but I also like did two steps in one. So you do here basically vs, and then you have x of n plus m is equal to j, comma, and then you put x of n plus k, where k is between 1 and m minus 1, is equal to v, and you have the condition x of n is equal to 1. So again, you introduce this x of n plus k is equal to v. You say you pick a time instant n plus k, which lives between n and n plus m, and you say that the chain is in some state v, where v is basically, it belongs to the the state space. It's one of those possible values of the discrete random variables that constitute the discrete time Markov chain. And then you say, okay, I have a conditional joint probability. I can basically apply the chain rule, and I can write it as the probability of x of n plus m is equal to j given, and so I conditional now on these two guys, times the probability of this conditional on xn is equal to I. Okay, now you can see that actually between quote unquote the Chapman Kolmogorov equations, which look very intuitive, they actually require the Markov property, because now you have this probability here. So this is the probability that at instant n plus m you are in state j, at n plus k you are v, and xn is equal to I. Now if we have something with the Markov property, we have a discrete time Markov chain, then here we have n plus m, here we have n plus k, and here we have n. Then by the Markov property, if you want to say, based on the previous lecture on the extended Markov property, basically you can eliminate this one here, because given it's like this is the present, given the present, the future and the past are conditionally independent, and so basically because k is between 1 and m minus 1, then given x of n plus k is equal to v, actually x of n plus m is conditionally independent of x of n, and so we can basically eliminate this guy and have a probability that basically that just this one, x of n plus m is equal to j, given x of n plus k is equal to v, which can, in a compact form, this is going from v to j in how many steps? This is n plus k, this is going in m minus k steps, which is this term here. And the other term is this probability. Okay, so again, the Chapman-Kolmogorov equation, it's like you write them, you can actually write them in two, so it's like they are hard to forget, right? So basically, you can write them, but basically they are not applicable like universally, despite their intuitive look. They require actually, and they also require homogeneity, right? They require that here you have n plus m, here n plus k. Then you say that basically things here will not actually depend on n, right? So they indeed require a homogeneous discrete time Markov chain. Okay, and as you can see also, like in Markov chains, like you can do things with summations. You can write down things using vectors and matrices, and all these are useful. Okay, sometimes it's more useful like to do things like as explicit sums. Sometimes it's nice like to write down like Bn plus n is equal to P of n to the P by P, the transition probability matrix to the m, and so on. Depends on the problem you are talking about. Okay, and now you can. What if you set n equals 0? So if you take this one. So what if you take basically this one here, and you put n equals 0. So if you put n equals 0, you get that you put n equals 0, and then you switch m to n. Okay, and then okay, you can write it like this, which will be better. It's correct what I wrote down, because it's just an index, but put n equals 0 here, you get that P of m, which is the state probabilities at instant m, is equal to the initial, so basically the state probabilities at instant 0. So those are like sort of the initial state probabilities multiplied by P to the power m. And this equation is like tells you that, if you're concerned is basically homogeneous discrete time Markov chains, to fully know the state probabilities at any time instant, you need two things. You need the transition probability matrix, which is the one-step transition, which contains the one-step transition probabilities, and you need to know what is basically the probability of the chain being in any state at instant 0. So you need sort of the initial distribution of states. You know these two guys, that's it. You can compute or you can know basically the state probabilities at any future time step. Okay, so this is again something that is very nice in homogeneous discrete time Markov chains. So our heroes are basically those two guys, B of 0, which is a vector that contains things like what is the probability that x of 0 is equal to I minus 1, what is the probability that x of 0 is equal to I, what is the probability that x of 0 is equal to I plus 1, and so on. So basically the initial PMF or initial distribution or whatever you want to call it, this is needed, and if you change those guys, you will get different distributions at other instance of time. So, but if you fix P of 0, and if you know the transition probability matrix, that's it for you. Again, because like making a transition in m steps is simply it requires the m step transition probabilities, and the m step transition probabilities are basically the TPM raised to the power m. Okay. Now let's go back to this business of eigenvalues and eigenvectors and see that it's not as it's not irrelevant. Actually, it's very relevant. So we said that there is a left eigenvector. There is a left eigenvector with corresponding to an eigenvalue 1. So basically, again, let's reconstruct our argument. So our argument is that the TPM by define, by how we define it, the TPM by how we define it is a matrix in which the elements are non-negative, they are probabilities, and the sum of each row is equal to 1. So it is the so-called Markov stochastic matrix. So this is number one. Number two, since the sum of each row is 1, then if you multiply this matrix by basically P is Markov matrix, and then P times D, which is the all one vector, is D, and we can put 1 here. So 1 is an eigenvalue, and so there is another eigenvector. Suppose that but this other eigenvector, if perhaps we are not sure whether its elements are positive or negative, because if that left eigenvector, the elements are negative, then they cannot be interpreted as probability, right? But suppose that somehow we discover that they are non-negative. Then in that case, this vector can be basically understood as a vector of probabilities, right? And remember that eigenvectors for any matrix can be scaled. You can do non-zero scaling of any eigenvector. So you can, like with MATLAB, get you have a matrix, you get an eigenvector with non-negative quantities, but perhaps the sum is not equal to 1. Not a problem. Just take the eigenvector and divide it by the sum of its elements, and you will get a valid eigenvector, the sum of whose elements is exactly equal to 1. Okay, so. Suppose that the left eigenvector is non-negative, so basically it's now something that you can treat as a distribution, as a valid PMF. Okay, so now we have QP is equal to Q, and Q is non-negative, and again you will choose a scaling such that QD, so QD, which is the sum of elements in Q, is 1, which means again that it's a perfect PMF. Now suppose that this left eigenvector is used as the initial PMF. So suppose that B of 0 is equal to Q. So what will be the distribution of the states at instant 1? So what is P of 1? So P of 1 is equal to, remember the general rule is that P of m is equal to P of 0, P to the power m. So P of 1 is B of 0 multiplied by the transition probability matrix. Now we initialize using the elements of Q vector, but the Q vector is a left eigenvector of matrix P corresponding to the eigenvalue of 1, and so this is Q. So P1 is also equal to Q. So what about P2? So P2 is, we can use actually that B1 times B, or we can write it as B0 times B squared. Okay, but we can actually use this one here. It's P1 times B, so it is QP, and this is Q. Oh, so basically what will happen is that if the matrix P, it has a left eigenvector corresponding to 1, but again, like, there is this issue, you know, that perhaps the corresponding eigenvector, perhaps it has, you know, are we guaranteed that it has non-negative components? Suppose so for now. If it has non-negative components, then it can be basically scaled so that it is a proper PMF. And now if you initialize your discrete-time Markov chain using that vector of probabilities, then what will happen is that at any instant of time, the distribution, the state distribution will be also Q, will also be, so the probability that x of n is equal to I will be the ith element in Q. In fact, you can show that it's not just that the state probabilities at each instant of time will be the same. You can actually show rigorously that basically the homogeneous discrete-time Markov chain will be a strictly sense-stationary random process. Okay, so that's the reason that if you find the left eigenvector with non-negative elements, this left eigenvector will have a name, and this name is the invariant distribution of the homogeneous discrete-time Markov chain, or the stationary distribution. It's called the invariant or stationary, and these two words mean something that is not changing, for the reason that if you initialize your homogeneous discrete-time Markov chain using Q, assuming that it exists, then the distribution will not change over time. The state distribution will always be according to the elements or the components of vector Q. And again, actually, you can show something stronger, that the full process as a random process is strict sense stationary. Okay, so now the question, do we have such a Q vector? And a left eigenvector corresponding to eigenvalue 1 with non-negative components. So it turns out that if your Markov chain, if the state space of your Markov chain is finite, you are guaranteed to obtain such a vector Q, which means that for all finite homogeneous DTMCs, basically they do have stationary distributions or invariant distributions. For the infinite dimensional case, I actually gave you an example earlier that actually there may not be a left eigenvector. Okay, so let's now go to this proof, which is that if your Markov chain, if it's finite in the sense that its state space is finite, or set S has a finite cardinality, then you are guaranteed to have a stationary distribution. And the nice thing is actually the way to prove this is by employing the surface of an old friend, the Farkas lemma. You know, remember the Farkas lemma was like, we used it to prove basically that you know, in the KKT conditions, right? And to prove a strong duality in linear programs. So now it is coming and to help us with the proof related to random processes. Okay, so before using the Farkas lemma to prove this statement here, that any finite DTMC has at least one stationary distribution. So at least one, because you will show one. I mean, perhaps there are more than one. So you know, there are no claims regarding uniqueness. Okay, so before doing that, any question so far? Okay, so a reminder, what is a Farkas lemma? what are our, basically, we need two things. We need a matrix, we need a vector, and the forecast lemma basically tells you that there are two statements. One is true and the other is false. They cannot be true at the same time, they cannot be false at the same time. So one of them is that there is a non-negative vector x such that v can be written as ax. The other statement is that there is a vector y such that the inner product of y and v is strictly negative, and the inner product of y and any column in A is non-negative. Okay? So if you want to apply the forecast lemma, you need to come up with a matrix and to come up with a vector, and then to apply to that matrix and that vector. And so what will be our matrix? Suppose that we have a homogeneous discrete-time Markov chain with a transition probability matrix that is P. And so basically I will construct matrix A, which is needed for the forecast lemma, and it is a matrix of size n plus 1 by n. And basically the last row in this matrix, is all 1. And basically the upper part of the matrix is the transition probability matrix transpose minus identity of size n by n. Now the v vector that is needed for the forecast lemma will be a vector of size n plus 1 by 1, and it is an all zero vector except that the last component is equal to 1. And let's start by assuming that actually the true proposition, the true statement is a statement 2. Okay, so we will have our y vector, and we will assume that actually this one is, that basically the second statement is true, which means that the first is false. We will derive a contradiction showing that the second statement cannot be true, and so by the forecast lemma, it is the first statement that is true. Okay, so suppose that the second statement is true, then vector y multiplied by v. So what will happen if you have the inner product of these two vectors? So every y will be multiplied by 0 except yn plus 1, it will be multiplied by 1. And this inner product should be strictly negative. So this means that yn plus 1, the last component in vector y, is strictly negative. Also, the second statement in the forecast lemma tells you that the inner product of yt and any column in A, okay, so you need to take yt, okay, so this is yty up to yn plus 1, and we need to multiply this by basically by any column in A. Okay, so you multiply by the jth column. Okay, so what is the jth column? What is the jth column in A? Okay, so basically A itself, its last row is always 1. Okay, so the jth column will end with a 1 here. This is true again by construction. We have all ones as the last row in matrix A. Okay, and then what are the elements above here? So we have P transpose. Okay, so P transpose. So basically the jth column here will come from the jth row. It will come from the jth row. Okay, so this will be bj1, bj2, okay, up to bjn, assuming that the number of states is small n here. Okay, and then there is a minus identity. There is a minus identity. So there is like a bjj, right? So there is a bjj from which we subtract 1, right? Because identity is just zeros everywhere except the main diagonal, and so there will be one element from which basically minus 1 is subtracted. So like as an example, if you cannot like see this, suppose that see this is b1 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 b2 b2 b3 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 okay. B transpose will be b1 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 b21 b22 b23 b31 b32 b33 okay. And suppose that we subtract identity. Okay, if you subtract identity, then we will have p11 minus 1, p12 b12, p21 b22 minus 1, and then p23, and then p31 p32, and then b33 minus 1. Okay, so we will get bj1, bj2, bjj minus 1, and then the others. Okay, so that's basically the inner this is so the column of interest, and now we will have basically we will multiply this vector y transpose. This is y transpose with basically this jth column. So what is the result? So the result is a summation k from 1 to n plus 1, yk, and then akj, so element akj in matrix A. But then, see that basically yn plus 1 is always multiplied by 1. Yn plus 1 is always multiplied by 1. So here it is. Okay. And then each yk for k from 1 to n is multiplied by bjk. By bjk. Here it is. And there is an extra minus 1 here, so basically there will be a yj that is also multiplied by minus 1, so minus yj. Okay, so again you can again do this product, and you get yn plus 1 because it's multiplied by the last element in the column, which is 1, and then there is basically this summation if you just focus on the transition probabilities. But then there is yj itself, it's not just multiplied by bjj, it's multiplied by gjj minus 1, and so you will get minus yj, and this is greater than or equal to 0. Okay, move those to the other side. Now, by Farkas lemma, remember that the inner product of v is between y and v is less than 0, and as a conclusion, it must be the case that the last element in y is strictly negative, and so this guy here is strictly positive. And so minus yn plus 1 plus yj is strictly greater than yj, again because this guy is strictly positive, minus yn plus 1. And now this is true for every column j, so we can choose basically we can choose the column that for which basically for which y is maximum. Okay, for which the value of y is maximum. Okay, so it's like we can take here the maximum. Okay, so choose j. So again, this is true. So remember, this is true for every j in 1 up to n. Okay, so apply to basically a value of the such that yj is the maximum of maximum y. Okay, we can do this again because this is true for every j. Okay, so we will choose the j that gives basically the maximum. Okay, then here is the contradiction. Okay, I mean, so far it's like, we are proceeding normally doing vector matrix multiplication and so on. So where is exactly the contradiction? So here is the contradiction that look to this part here. Okay, it is those are the bjk is like a non-negative quantity, so those are greater than or equal to 0. So this is less than or equal to, I can upper bound, I can basically okay, let's say it this way. I actually, okay, so this is good. I can upper bound each yk by its maximum, right? So basically this is less than or equal to, and then I have summation k from 1 to n. Then you have the maximum I of yi, and then bjk, right? So I replace each term here by its the maximum term, I from 1 to n. I can do this again because the bjk's are non-negative, and I can just upper bound each term by the maximum value in basically the first n components in vector y. And now the maximum is some number. Okay, I can pull it outside, maximum I, yi, and then we have summation k from 1 to n bjk. And then what is this summation here? We are summing, so basically we are fixing the row in matrix, okay, in matrix P, right? bjk, and we are summing k from 1 to n. This is exactly sum of the jth row in the transition probability matrix, and any row in the transition probability matrix gives you 1, and so this is equal to maximum I y. Okay, so this is the trick here. So basically, again, you reach it this one, but then you say, okay, I will have this summation. I will upper bound each y by the maximum y, and then I will take this maximum outside the sum because it's just a number now, and then I will do the sum, which turns out to be the sum of a row in the transition probability matrix, and that's 1, and so I get the maximum. And so, but we have a strict inequality here. So now we prove that a number is strictly greater than the same number. It's like, you know, we prove now that 5 is strictly greater than 5, or that 7 is strictly greater than 7, or whatever number is strictly greater than the same number, which is nonsense. Okay, so that's a contradiction, and by this contradiction it means that this second statement cannot be true, and so it is the first statement. It is the first statement that must be true. So we do have a non-negative vector. We do have a non-negative vector such that I take vector v, which by construction is the all zero vector with 1 as the last component, and then I can take matrix A, I can take this vector v and write it as ax, and x is non-negative. Okay, so what do we learn from here? We learn that you know, if we do this multiplication, you know, d transpose x will give you 1, which means that the sum of components of x is equal to 1, and remember that x is non-negative. Okay, so x vector is a proper PMF, right? It is something that is non-negative, and the sum of its components is exactly equal to 1, and so it can be used as a PMF. That's cool, but more importantly, now if you take those first n rows in this matrix and multiply them by x, then P transpose x minus x is equal to 0, which if you take the transpose, then x transpose P is equal to x transpose. So that's a row vector multiplied by B equal to the same row vector. And so, you know, and so basically for any matrix, finite dimensional, I mean, because like in the Farkas lemma, if you go to the proof of the Farkas lemma, it's like inherent in it was basically that we are talking about finite dimensional matrices. Now, for every finite dimensional transition probability matrix, or in other words, for every finite dimensional homogeneous discrete-time Markov chain, you are able to find at least one vector that is non-negative. It can be used as a PMF, and if you use that vector to initialize the homogeneous discrete-time Markov chain, the discrete-time Markov chain will be a strict sense stationary random process. In other words, that for every finite dimensional DTMC, there exists at least one stationary distribution or one invariant distribution. Okay, and so that's the proof that you are guaranteed to be able to find this distribution. Keep it in mind, whenever I say invariant or stationary distribution, I mean I'm talking about this. I'm talking about the distribution that if you use in initializing the chain, then at each time instant, the state probabilities are exactly the same. Any questions? Okay, so in Markov property, we condition on the present, like xn is equal to I. What if we have something like xt? What if we condition on xt rather than xn, and t is a random variable? Okay, so you know, this is a case of interest because sometimes, especially when we study random walks, sometimes we condition on x of something, and this thing itself is a random variable. So, does the Markov probability hold? Property, sorry. Does the Markov property hold? So it turns out that yes, but you need a specific type of random variable, which is a stopping time. Okay, so the same, the same stopping times we talked about when we studied renewal processes. Now, it turns out that again, and this is very useful again when we study things like random walks. Here is, and this property is called the strong Markov property, which means that you do not actually need to condition on x of 5 or x of 17 equals to some of its possible values. You can condition on x and then the subscript of x. The instant of time itself is a random variable. So let TP is stopping time with respect to a homogeneous discrete time Markov chain. And now let basically the stopping time, it's a non-negative integer, and so it can be a defective random variable. So it can take the value plus infinity, or some people call it extended random variable because we allow it to take the value plus infinity, which is not a real number, but it is an extended, it belongs to the set of extended real numbers. And so here is the story. Given that t is finite, given that the stopping time is finite, and that x sub t is I, here is the key. That now you are saying that it's not x of some fixed time instant. You have x of a random variable is equal to I. Then x of t plus k for k greater than or equal to 0 is indeed a discrete time Markov chain. In fact, it is a Markov chain with the exact same TPM as the original Markov chain. Okay, given that the stopping, given that the random variable that we use here is stopping time. Okay. Moreover, x of t is equal to I, x of t plus 1 up to x of t plus n. Those random variables, or this event that depends on those random variables, is independent of whatever happens before t. Okay, so how can we show something like this? Let h be an event in terms of x sub 0, x sub 1 up to x of t minus 1. So this is like the best. But again, the new thing is that t itself is a random variable. Okay, let's start doing our analysis with this probability here, which is like, it's not obvious why we do this. So again, like, you need like to, if you are like trying to prove these statements on your own, you will have like to experiment, many times before like you put yourself on the right track. So we will study this event here. X of t plus 1 is equal to I1, x of t plus 2 is equal to I2, x of t plus n is equal to In. Okay, so those are, time instants after t plus 1, t plus 2, t plus 3, t plus n. And then x of t is equal to I, but then I put here t is equal to m. So I will include the event that basically t is fixed and is equal to m, which is sort of like, again, like thinking about, or let's put it this way. You do this because, till now we don't know what to do if we are conditioning in x, if we are conditioning on x of something that is random. And so what we will do is that we will condition on x of t, but we will fix t for a while, right? Because if we fix t, then this is the old business. Okay, and then we can use the Markov property, we can use the extended Markov property and stuff like this. Okay, so that's the trick. Because we don't know, if we just leave t as a random variable, this thing here becomes, something that we cannot handle. So we will put x t is equal to I, but then we put t is equal to m. And then we have h, which is an event that is specified, or that is basically defined in terms of all those guys up to t minus 1. Okay. Okay. Now take this joint probability of many things and like do the chain rule. So basically take those guys. Remember that here you have an event that big T is equal to small m. So because you have this, you can actually replace each big T with small m, because you have this guy here that big T is equal to small m, And so you can write down those guys as x of m plus 1 is equal to I1, x of m plus 2 is equal to I2, all the way to x of m plus n is equal to In. Okay. And then you can, so you take those guys, you condition on the remaining ones. So xm is equal to it is equal to m and h, and of course you need to multiply by basically the probability of those you conditioned on. So that's classic, second line is classical probability. Okay, so now what you do is, okay, so perhaps perhaps I need to do this in slow motion. Let's basically like reveal what is going on. H defined in terms of x0, x1, x2 up to xt minus 1, and now we are fixing t as m, so this will go up to xm. Okay, minus 1. Okay, t is equal to m. T is a random variable, but it's not any, one of those random variables that you randomly encounter in the street. It is a stopping time. So stopping time by definition, this one, because t is a stopping time, then it is defined in terms, or then, let's put it this way, then event t equals m is independent of xm plus 1, xm plus 2, and is specified knowing x0, x1 up to xm. Okay, so again, you need this because like if t is a random variable, like sort of depends on x of m plus 1, then this is a different story, right? So I need it to be a stopping time, as you will see. And here we have x of m, which is fixed at I. So look here. So this guy is like a future. We are talking about the Markov chain at time instance m plus 1, m plus 2 up to m plus n. We are conditioning on x of m equal to I. What the other things we are conditioning on basically depend on stuff from x of 0 up to x of m minus 1 and x of m. Why is that? Because of two things. H, by definition, I'm using H in this proof by saying it is an event that is specified or that is defined in terms of x of 0 up to x of m minus 1. And the t is a stopping time, and so by definition, t equals m, it is something that, it is an event that is fully characterized by x of 0, x of 1 up to x of m minus 1 and x of m, and x of m is given equal to I. So now we have this conditional probability. Now by the extended Markov property, again, so we have a future, it's like f in the previous lecture, this is x of m is equal to I, and this is like the past, and so by the extended Markov property, the future and the past are conditionally independent given the present. So I can write down this conditional probability, or I can rewrite it, eliminating these two guys, and just keeping x of m. Okay, so this is the trick. The trick is to start your proof by having an x of t equals I, but then fix a t so that you can exploit your existing knowledge about the extended Markov property. And while doing this, you will see that why do we need the random variable t to be a stopping time? if it's just a general random variable, we are lost. We will not be able to go anywhere. But because t is a stopping time with respect to the sequence x of 0, x of 1, x of 2, and so on, then basically t equals m is something that is defined in terms of only x of 0 till x of minus 1 and x of m. Everything that, from xm minus 1 and below can be ignored because of the extended Markov property, and we just keep this guy. Moreover, we are, our interest is homogeneous discrete time Markov chains. So basically, everything here, we have m plus 1, m plus 2, and so on. But for a homogeneous DTMC, things do not depend on basically the absolute time. The transition probabilities, they depend on time differences. And then by homogeneity, we can just set m equals 0. And so we can rewrite this. We can replace this m by 0, this m plus 1 by 1, m plus 2 by 2, and so on. Okay, so we have this probability here, which is like, it's like you have the original discrete time Markov chain. You start at I, and then, at instant 1, you are in state I1. At instant 2, you are in I2. At instant 3, you are at I3. Up to at instant n, you have In. Okay, so sorry for something that basically n, so on the previous page when we did the Farkas lemma, n was the number of states. Okay, now n is a time index. So sometimes I use it as the number of states, sometimes as the time index. Okay, it's confusing. So so you will understand it from the context. Okay, it's annoying. Perhaps the number of states should be given like another symbol, perhaps basically the cardinality of S denoted as such or as such. But but keep this in mind. So don't be confused. N sometimes is used as a time index, and sometimes I use it at the number of states. Okay. Not a good choice, admittedly speaking. Okay, then you have basically this term here, and so what you will do is that you will take the original quantity, which is this mysterious quantity, and you will sum over basically m from 0 to, so basically you will sum over m in basically 0 union the natural numbers, the positive integers, and you will divide by this. Okay, and so what will happen? So let's focus on this. Note that after applying homogeneity, this thing here becomes independent of m. So if you sum over the possible values of m, nothing really happens for this term. But what about the other term? The other term, so it is equal to this. Okay. It is equal to this, and now what you will do is you say x of m is equal to I and t is equal to m. I can put x of t is equal to I and t is equal to m again because these are equivalent, because t is equal to m. Now what will happen if I sum this thing for m in the natural numbers union 0? Union 0. Okay, so 0 from 0 to 1, 2, 3, 4, 5, and so on. So what will happen? What will be this event that t is equal to m? From your previous lives, typically, if you do this summation over t equals m, t will disappear. Because most likely in previous life, you dealt with basically non-defective random variables or ordinary random variables that only take basically finite values. But here, if you sum over the finite values of m, what I will do is that I will basically put t less than infinity. Again, it's like, we will see later why, basically, we can have, or we need to use defective random variables. Okay, so by doing this sum, it is not that t will disappear, it's that t will be t less than infinity, which means that t will be some finite number 0 or some positive integer, and so you get this probability, and when you divide by x of t is equal to I and t less than infinity, you basically get the conditional that h is basically like this. Okay, so what you will do is that you will do this to this mysterious step here, this probability we started with. Again, you sum over m from 0 to infinity, you divide by basically x of m is equal to I and t is equal to m, and you will get this nice result here, that this joint, this probability, this conditional probability here can be split into, so that the past events are now separate. So basically, so here I have given that x of t is equal to I and that t is less than infinity, then the future is conditionally independent of x of 0, x of 1, up to x of t minus 1. Remember, this was event h. Okay, and so you have the Markov property. And now this is called the strong Markov property because you are conditioning on x of t. But t must be stopping time.